All right, the electron configuration idea. So here's our topic for today. Okay, the electron configuration idea deals with Bohr. All right, it deals with the Bohr concept that we learned yesterday, based again on the fact that atoms are made of electrons. Those electrons are arranged. Arranged is just a fancy word for they are organized. All right, they are organized in what we call energy levels. Okay, so again, what we're dealing with here is the concept, and I'll get out of your way here in a moment. All right, is we're basically dealing with what we learned yesterday. Now we're adding to it. So I don't want you to think that electron configuration has nothing to do with what we learned yesterday, because everything we know about electron configuration today that we're going to learn has to do with what Bohr discovered that day, that he discovered that electrons are not just roaming around there any way they want to. They're following set pathways that they follow. Okay? What?
Does that say you?
Yes. Couldn't tell what she said. I need somebody to translate. I was expecting you to do something there, Country Mark. All right. So, electron configuration deals with the Bohr ideas. Okay. So maybe I should write there ideas. Now, his main idea is again that electrons are arranged in energy levels. Okay, energy levels, and so again, there are different orbital paths. There are different pathways that electrons can take. All right, those pathways are what we call the energy levels. And the reason why we call them energy levels is because different paths require different amounts of energy, which means if, like, in other words, you have 3 different levels of classes in high school. Okay, we'll talk about like in the realm of the physical sciences. Like I told you, there are 3 different levels based on the 3 different types of students. If you are this kind of student, then for a physical science credit, you should take honors chemistry. But if you're not an honors chemistry student, but you're also not a standard student, all right, then you should take chemistry. But if chemistry is too much of a challenge for you, all right, then you have a more basic level, which is physical science. All 3 classes, 3 different levels, but they all satisfy the same physical science credit that you need to graduate. Well, guess what? Energy levels are exactly that. They are levels. But at one level, you have so much energy. At another level, you have a different amount of energy. And those electrons, like some students, they can change from one level to another level, but sometimes they come crashing back down again. And so that's what we're dealing with here, is that these electrons are arranged. In other words, today's focus word, all right, today's focus word is arranged. We have to learn how are they arranged, all right? And one of the levels, okay, one of the levels is energy levels. But much like anything else, when you walk into a school, when you walk through the front door of the school, do you see every student just walking around the school and all teachers just, doing whatever they do everywhere in the school? Like, do you just go around and you just say, hey, look, there's a whole group of kids over there. Well, some of those kids over there are kind of science kids, and some of those same kids in that group over there, they're kind of like English kids, and some of those kids over there, they're like art kids. All right? Is it kind of mixed in? Everybody's all mixed in together like that? That's a yes/no question. Okay, some of you saying yes, some of you saying no. All right? Well, who said no? Jared? All right? Why do you say no?
It's like what you like, that's who you're going to hang out with.
Okay? So I'm not doing a good job. I mean, because you're not wrong. I'm just saying I'm not pointing my point across very well. All right? What I'm saying here is this. When you walk through the door, is the school one big room where everybody's there and everybody can see each other and all the teachers can hear each other while they teach?
Mm-hmm. Wait, no.
Okay? No. Meaning, once you walk into the school, there are designated areas, right? Like there's an area for the office, and then there is an area that we call the 100 hall. There's an area that we call the 200 hall, and there's another area that we call the 300 hall. There's another area that's called the 400 hall, right? And then, so that's one area that everything is organized or arranged in. But then if you go into the 300 hall, then you have another set of arrangement in the 300 hall. Those arrangements are called classrooms. And in one classroom, you have an English class going on. In another classroom, you have a math class going on. In another classroom, you have a science class going on. So that everybody isn't mixed together in one room, hearing all 3 teachers teach and getting confused by things. Everything is kind of separated out, organized to make it more efficient. Well, that's the same thing Bohr said. Bohr said that these electrons aren't just floating around everywhere doing whatever they want to do. They're organized. They're put in certain places to make it more efficient. One of those places is the energy level. But there are levels within energy levels. All right? Those levels within the energy levels are called orbitals. Okay? And so what I need you to know is this. There are 7 energy levels. Okay? There are 7 energy levels. There are 4 types of orbitals. And each orbital is based upon a certain section, based on how many electrons you're going to deal with here. All right? Now, if you go into a classroom, like if you went into right now to Miss Fain's room, are you going to have the exact same students, the exact same number of students that are in my classroom? No, because it kind of just depends, right? Well, that's the way the orbitals work. That's the way the energy levels work. Energy levels don't have all equal number of electrons because they're not all equal. Orbitals don't have all equal number of electrons because they're not all equal. All right? Everything has its own set amount. And what we need to kind of show you today is what are those amounts, okay? But first of all, let me give you the 4 types of orbitals, okay? Because that's where the configuration comes into play. Like these are the things you're going to be dealing with today tremendously. You have an s orbital, you have a p orbital, you have a d orbital, and you have an f orbital, okay? Now, in the case of the s orbital can hold 2 electrons. All right? The p orbital can hold 6 electrons. The d orbital can hold 10 electrons. And the f orbital can hold 14 electrons. So every orbital holds a certain amount. And every orbital is found at a certain level. So the levels in the orbitals, just like, again, every section of the school, like there used to be one time before you guys were ever here, probably before you guys were ever in middle school. All right? There used to be a time where basically in this school, if you're an English teacher, you taught in the 100 hall. All right? If you were a math teacher, you taught in the 300 hall. And if you were a science teacher, you taught in the 400 hall. And history teacher was the 400 hall. Like computer classes were in the that 100 hall area. Allied health, right? Those health classes, they were taught in the 200 hall, that section right there. Like it used to be organized in that particular kind of way. All right? So, there's always a arrangement for how things are run to make them run more efficiently. And that's what we're trying to understand today. The Bohr idea of electrons can be demonstrated by the electron configuration that we're going to deal with here. Take a look at your periodic table. So go ahead and take out your reference sheet. All right? So you need your reference sheet. Please take that out at this time. And that stands for electron because it's got a negative symbol. All right, so that's my symbol. Yeah, thank you for asking. All right, so what I'm going to show you here may not make sense now, but it might make sense again when I bring it up to you again. But I feel the need to go ahead and bring this to your attention because I'm not sure how much of this right now is clicking. Okay? So we're looking at our periodic table. Everybody has this written down, correct? Because I got to erase it so my periodic table can show up on the screen. All right? Elijah, I need you to do me a favor and go ahead and turn on that projector for me, please. All right, so what I want us to notice here is this. When we look at our periodic table, okay, which is popping up here on the screen, we can see that there is a particular type of layout here. All right. Now we can see one of the most common things that people notice are these elements down here at the bottom that have kind of been broken off or separated from the rest of the periodic table. All right. So what I want to do right now is to kind of start us off by looking at this. All right. Take a look at these elements that have been kind of separated from the rest of the periodic table. All right. When you look at them, what I want you to notice here is this element here is element number 58. All right. 58. And then this element over here is element number 71. So if you notice, the last element on the periodic table right here is 112. So if you notice when we go down here is not a continuation from the end of 112, because if it were, it would start with 113. All right? But if you look at it, this is 58. 58 then is before 112, so that means these elements here are actually within this area of the periodic table, but they've been separated away. If you notice, we go from element 56, 57 to 72, which means this row of elements right here that I'm looking at actually would be injected right in there. Okay? That's where it actually would be filed. Okay? But there is a reason why they've been separated out. All right? And we don't need to worry about that reason today, because there's a reason for that we'll learn in test 4. But right now, we are looking at that there is a set right here that has been sectioned away. Now, I want to look at the section, because when I look at this section and I look at this row of elements that I see right here, well, go ahead and count on your periodic table how many elements are in that row of elements. Okay? So you count for yourself, because if you don't see it, it will never click. Don't say it out loud when you get it. Just count and see how many you got. If it's taking you this long to count, then you're slow. Damien, how many are there? 14. Okay? There's 14. All right? There's 14 elements in that row. 14, right? How many electrons does the F orbital hold? 14. So all these elements right here would utilize the F orbital. When we're having to arrange things, we would have to use the F orbital for these elements, because F orbital holds 14. These guys have 14, right? Now, take a look over here at your periodic table. Most of the time, people have this issue here, this big gap that's right here between these two sections. I got a section over here on the left, and I have a section over here that's on the right. And I have this big gap in between, right? If we take a look at this big gap, the big gap begins with this element right here. And it ends at this element right here. So if I count from outline box to outline box, how many elements would I count in that section?
10.
Okay. Country mark? 10. All right, there are 10. So notice, all the elements right here, right? We have 10 in a row. What orbital holds 10 electrons?
D.
The d orbital. So all of these elements right here, we would consider in the d orbital, because they are going to utilize the d orbital, because they're in that section that has 10. Just like these will be the f's, because they're in a section that has 14. Everybody connecting that so far? Starting to see it? All right. Now, the other part that we need to look at, where's my eraser? Here's my eraser. Is what is on each side of the big gap, right? When we look at the gap, we have this section over here, and then we have this section over here. Well, if we look at this section, right, how many do we have in a row? 2. What orbital holds 2 electrons? The s orbital. If I look over here at this section, right over here, how many do I have in a row? 6. So what orbital uses the 6 electrons? The p. So here's what I know. All these elements right here, they make up the s orbital. All these elements right here, they make up the p orbital. All these elements right here, they make up the d orbital. And all these elements right here, they're going to utilize the f orbital. Okay? Carlos.
I feel like you're about to clean this right now anyways, but what about the top 2?
What about the top 2? When you say the top 2, you talking about that?
Yes.
Those are not an element because they don't have a symbol inside of them. Dark gray boxes are not elements.
Okay.
They're headings. They're headings, okay? Which a lot of people still count as elements. All right? Yomani.
How about the hydrogen and helium?
What about the hydrogen and helium?
In a row, like.
Gotcha. We'll deal with that when we get to that because, again, what we're going to notice about our periodic table is this. It helps us learn a lot of trends or big ideas, but in science, we never say never and we never say always because there's always an exception. So, like, in this case, we can apply this to many and a lot of elements, but there's always going to be a weirdo in there somewhere. Right, Julia? All right, so, therefore, that's why we're going to deal with the big idea, and then when a weirdo comes up, we're going to spot her and name her. Okay?
But it's still included, right?
They're still included, yeah, because they're gonna when we do it, we're gonna do configurations for them, and then you'll see kind of where they fit. But they are a weirdo, so that's why we don't want to. I don't want to give too much because right now I need you to see the big idea. Because once you see the big idea, it's easier to understand or tolerate a weirdo. But right now, if all you focus on the weirdo, then you ain't gonna understand the big idea. Okay? So now, an electron configuration. All right. In electron configuration, there are 3 types of electron configurations. So, when we look at electron configurations, there are 3 types. The first type is what I call, so there are 3 types of configurations. Type 1 is what we call an orbital notation. Type 2 is what we call a standard notation. And then type 3 is one that we call a noble gas configuration. Okay? My goal today, which it's going to be reached, is to make sure you walk out of here knowing 1 and 2. Number 3, I can always come back to later. So I'm not going to force number 3. Because number 3, if I were to force it, might confuse you enough to screw up 1 and 2. So my goal today is 1 and 2. If I can get 3, great. If not, I'm not going to force it because that can screw up other things. All right? So now, these are configurations. They involve energy levels and they also involve orbitals. Okay? There were 4 types of orbitals, and that's literally what I just showed you on the periodic table, right? How many different types of energy levels, or how many energy levels did I say there were? 7. Okay? Go back to your notes, all right, where we were writing down about energy levels, which you're in your notes right now. Okay? And there are 7 energy levels, but there are 4 types. So I'm putting this little box here in that section where I was doing energy levels. Okay? Because there are 4 types of energy levels. There is the kind that can hold 2 electrons. There is the type that can hold 8 electrons. There is the kind that can hold 18 electrons. And there is the kind that can hold 32 electrons. All right? This will come into play. This will be much more important for you to remember on Monday. All right? When we're drawing atom models, it's going to be much more important that you remember this whole concept of 2, 8, 18, and 32.
Wait, it's 4 types of what?
Energy levels. So, let me kind of say it again, so that way in case you wrote it and then you didn't hear it. There are 7 energy levels, but there are only 4 types of energy levels. The one that can hold 2, the one that can hold 8, the one that can hold 18, and the one that can hold 32. There are 4 types of orbitals. The S, the P, the D, and the F. Okay? So that's kind of what I'm trying to get you to see right now. However, though, if we take a look at it, right, we're going to kind of show you how this works. So if we talk about the energy level, okay, if we talk about the energy level, right, there is a kind that can hold 2 electrons, right? Is there an orbital that can hold 2 electrons?
Yes.
What is it?
Yes.
The S. So guess what? Here's what I know. If I'm using the energy level that can hold 2, I know I'm pretty much using the S orbital. Because remember, in the school, are there hallways? Yes. Are there hallways with classrooms? Yes. Are the hallways bigger than the classrooms? Yes. But can you be sometimes in a hallway where you're the only classroom? Yes. And that's what we see right here. The energy level, all right, is the hallway that has 2, but it also has a room that has 2. That orbital is called the S. What's the second type of energy level? 8, right? All right, so my question, this is a yes-no question. Is there an orbital that can hold 8? That's yes or no?
Yes.
No. Okay? Because we said there was a 2, there was a 6, there was a 10, there was a 14. So there is not an orbital that can hold 8. Right? However, though, can I combine orbitals to get 8?
Oh, yeah.
Who can I combine? S and P. So you see how these things now are starting to work together? All right? So now there is an electron energy level that can hold 18 electrons. Is there an orbital that holds 18 electrons? No, but can I combine it? How would I combine it? All right, an S, a P, and a D. Because 2 plus 6 plus 10, that's 18. You can kind of figure where I'm going to go next, right? The 32 energy electron, right? I'm sorry, the 32 electron energy level is probably going to be made up of what? S, P, D, and F. Because when you add them all up, you get 32.
Could it be like S plus
You'll see. Ready? Right now, we're getting close to just doing a configuration where you're going to see how it works out. Because right now, where I have to get to, now that I'm getting you kind of to see how all this fits on the periodic table with what I'm putting here on the board, now what I got to do is I got to give you the rules. Okay? And there are 3 rules. You need to look at these 3 rules. Because, just like significant figures, if you choose to not remember the rules, then you're choosing to say, I don't care if I'm right. Okay? The 3 rules are in your reference sheet. I'm sorry, not reference sheet. They're on your periodic... Let me try that again. They're on your vocabulary sheet. The first rule we need to look at is the off-bow principle. Okay? And the off-bow principle says this. The off-bow principle says, when you do a configuration, you start with the lowest level orbital first. Okay? When you do a configuration, you start with the lowest level orbital first. The lowest level are the ones that have the lowest numbers. Which orbital had the lowest number? So that means you're always going to start with an s orbital. Because before you can go to a next orbital, you have to deal with the low. In other words, when you started math, did you start with calculus or did you start learning numbers? You started learning numbers. Because it's hard to do calculus when you don't even know what a 1 and a 2 and a 3 is. Right? So it's the same idea. We got to start with the lowest orbital first. So that's the off-bow principle. All right? The off-bow principle can be summarized using this particular chart. Now, if you choose to use this, great. If not, it doesn't matter, because the key here is you need to make sure that you work this out. The chart that we're going to use here is called is got all the orbitals here on there. All right? We got 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Why do I have 7 s's? Because how many energy levels did I say there were? 7. If you look at your periodic table, just for clarification, if you look at your periodic table, who's the first element on the periodic table? Hydrogen. Well, there's my first row. Okay? So ready? Is there a row underneath it? Yes. Is there a row underneath that one? 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 Yes. And then there's no row underneath that one because it's detached. Right? So how many rows did I just go through? 7. That's why there's 7 energy levels. There's 7 energy levels because there's 7 rows on the periodic table.
What does that say?
Okay? It says off bow. It's on your vocabulary sheet. All right? So that's why I've given you 7 S's. All right? I've given you 7 S's because there are 7 rows. Remember, what side of the periodic table did I say was the S section? The left, right? So I just counted on the left side 7 rows, correct? That's why I got 7 of them. Okay? Now, on the next orbital will be the p orbital. The p orbital will start at the 2 level. Okay? It will start at the 2 level because helium, all right, here's the weirdo. Helium that's on that right side belongs on the left side. Okay? It belongs on the left with the S's. But it's not, for a reason that we will clarify later. Okay? So there's a reason that is weird. Unlike, there's no reason for that's weird. So, 3p, 4p, 5p, 6p, 7p. All right? So therefore, that's how that works. Now, there's a whole reason we're doing this is because I'm trying to give you something that you can use, because otherwise you got to memorize it. All right? And it doesn't matter as long as you know it. All right? Now, the next orbital is the what? Hello? The d orbital. Okay? The d orbital starts at the 3 level. So we have 3d, 4d, 5d, 6d, and that's it. All right? There is no 7d. All right? Then we're going to go to the f orbital, right? In the case of the f orbital, you only have 2. It starts at the 4f and the 5f. Okay? Now, here's where it kind of becomes important. Now, notice I have everything nicely written in columns. Notice I have everything nicely written in rows. And the reason for that is because when we use our orbitals, all right, they go in a weird kind of order. All right? So, the first one that we're going to use is the 1s. After the 1s is the 2s. Then after the 2s is the 2p. Then after the 2p is the 3s. Then after the 3s is the 3p. But here's where it becomes confusing. Because you say, oh, that means the next one's going to be the 3d. No, the next one's going to be the 4s. Then the 3d. Then the 4p. Then the 5s. Okay? And then the 4d. Then the 5p. Then the 6s. Then the 4f. Then the 5d. Then the 6p. Then this, you see what I'm saying? Like, it starts getting confusing. So that's why this chart helps us out a little bit. So what I do usually here is this, all right? And just to kind of, just to show you what I'm showing, what I'm looking at to make sure, all right, is this. When you look at that diagram right there, okay? You see that diagram? See how they have those little arrows? Those arrows are showing you kind of the pathway of what orbitals we use in the order that we use them. Okay?
Can you like draw them in, highlight them in or something?
I don't care how you, I mean, I don't mean that rude. I mean, I don't care what you got to do to be successful. Everybody's different in how they take notes. Some people don't even take notes. All right? But the bottom line here is this. I didn't mean to do that. Right? Like, that's what we're looking at right there. I'm trying to show you how those arrows move. So when you look at it, it's basically is I go here, right? Then I backtrack. Then I go here. Then I backtrack. Then I go 2p, 3s. Then I backtrack. Then I go 3p, 4s. Then I backtrack, right? Then I'm going 3d, 4p, 5s. See how everything's at an angle? That's not side to side. It's diagonal. Okay? Then after that, it's 4d, 5p, 6s. Then it's 4f, 5d, 6p, 7s. Then it's 5f, 6d, 7p. Like, that's what this chart's trying to... This chart is kind of help you say, if I have them arranged, if I go diagonally, then I know when things get complicated, what my orbital order should be. Or, ready? I mean, this is what I'm saying. Like, if this is complicated because some of you can't be that neat and organized, or you can just memorize the order. It doesn't matter. You know what I'm saying? For some people, this works well. For some people, memorization works well. And if you got another system and you get the answer right every time, I don't care. Use it. I'm just saying, for some of you, if this helps, use it. If it doesn't, don't. Because you ain't got to do nothing. But, I can die. Got it? So, everybody see the diagram there? So this is something that, again, you either want to have in your notes, like you've already written this part, because you wrote it with me. Whether you draw the lines or whether you memorize how the lines go, that's kind of up to you, all right? Because I don't want it to get too messy on your notes, because then you ain't going to know what you're looking at. So, are we good right now? I'm going to put that back. Can I cover my screen, or is somebody still doing the lines from the blue diagram? Okay, well, nobody said nothing. Okay. So now, that's the off-bow principle. Okay? The off-bow principle says, when you're doing a configuration, you better do 1s first. Well, what if I got more? Then you go to 2s. What if I got more? Then you go to 2p. What if I got more? Then you go to 3s, right? Like when you say, what if I still got more? Well, then you go to the next one. But that order that I just ran through, that's the off-bow principle. That's the order. If you go out of order, then you're wrong. Okay? If you go out of order, then you're wrong. So memorize or create. Doesn't matter to me. Rule 2 is the Pauli exclusion. The Pauli exclusion says this. Okay? This is what the Pauli exclusion says. It says each orbital I'm not going to write it. I'm going to show it. Okay? The Pauli exclusion principle says this. So let's take a look at the p orbital, right? The p orbital can hold how many? 6. Okay? It can hold 6 electrons, right? But what the Pauli exclusion principle says is this. It says that in this orbital, there are suborbitals, bless you, that can hold 2 electrons each. Okay? Kind of like in my classroom, I have other rooms. All right? But those other rooms are not as big as my classroom. But they make up the classroom. So, if my orbital can hold 6, so here's what I need you to catch on to. If the p orbital can hold 6 electrons, then how many suborbitals would there need to be? 3. Because if each suborbital can hold 2, well then I'm going to need an orbital for these 2, an orbital for these 2, and an orbital for these 2 so that I have 6 in the end. All right? So the way it looks here is a p orbital would look like this. P, P, P. With this one being able to hold 2, this one being able to hold 2, and this one being able to hold 2. All right? There are levels within levels within levels. It's kind of like computers when if you're organizing your Windows PC, you have a file, and then there's a file within a file within a file within a file. Okay? That's kind of how it works. Some people don't even create files. But nonetheless, I'm just saying there's files within files. All right? So that's what the Pauli exclusion principle says. None of these rules are really going to make sense to you right now because you don't get it until you start to do a configuration. We still haven't done a configuration yet. All right? However, the third rule is Hund's rule. And Hund's rule says you must go up, up, up before you can go down, down, down. You must go up, up, up before you go down, down, down. Okay? So what happens here is this. All right? When we're doing the Pauli exclusion principle, this orbital can hold how many? 2. What the Pauli exclusion principle says also is this. I will represent an electron using an arrow. Okay? I will represent an electron using an arrow. However, an electron, this is important. We said it yesterday, but I don't know if you remember. An electron has what charge? Negative. If I take a negative and put it next to another negative, what are they going to do? They're going to go apart. So therefore, if this orbital here were to, let's say right now, they all have an electron, right? If I was going to put another electron here, the other electron has to go in the opposite direction. Because when they get by each other, what are they going to do? They're going to go in the opposite direction. Okay? And so what Hund's rule says is this. If I have 4 electrons in this orbital that can hold 6, what Essence would want to do, because she's female, is she'd say, well, let me go ahead and put 2 here and 2 here. That way it's nice and even. Right? 2 and 2. Perfect. Great. Right? But Hund's rule says no. Hund's rule says before you can put a second one in an orbital, you got to give each suborbital 1. So that's why you have to go up, up, up before you can come back and put another one in another box. So you can't just say, oh, there's 4, 2, 2. Nice and even. No. It's got to go 1, 1, 1, and then you put a second one in the next one. All right? If there were 5, it'd be 1, 1, 1 before you can add the second and the second. All right? That's what Hund's rule says. So those are the 3 rules. The 3 rules are off bow, you better go in the right order. 2, Pauli exclusion principle, which means that each orbital better be broken up into its doubles. All right? And then Hund's rule, which says before you can go and put a double, you have to give everybody a single. Okay? So now, let's get to work. Let's do a electron configuration. All right? So I'll say it like this. Cameron, I don't care. You pick any element 1 through 36. Challenge me.
Titanium.
Titanium. Great. Everybody find titanium, all right? Element number 22. Element number 22. Okay? Now, the first question we got to know is this. If I'm laying down the electrons, I kind of need to know how many electrons titanium has. Well, what element number is titanium?
22.
Then that's how many electrons it has. Okay? So for right now, all you need to know is the element number is the electron number. So it's got 22 electrons. So we good? Now I got to lay them down. What's the first orbital I'm going to use? S. All right, specifically 1s. So therefore, there's my 1s. How many can the 1s hold? 2. So therefore, how many do I got again? I got 22, right? So I'm going to put how many of those 22 here? 1 and 2. 1 and 2. Opposite directions. Because remember, they are electrons. They're negatively charged. When you put them next to each other, they're not going to attract. They're going to repel. Because that's what happens naturally. Opposites attract, like kind repel. All right? So now, I've placed 2 of my 22. How many left? 20. Okay? So now I'm at 20. So I still got more. What's the next orbital I'm going to go to? 2s. So now I'm going to go over here, and I'm going to write 2s. How many can the 2s hold? 2, because it's an s orbital. So it can hold 2. So I'll put 1, 2. How many do I got now? 18. All right? So I still have more. But let me stop there for a second. Everybody following so far? Anybody have any questions right now? Everybody sees right now that I have right now the only thing I have used is the off-bow principle and the Pauli exclusion. I have gone in the right order, and I've made sure that they have been put 2 in a box, 1 of opposite spin. Okay? I have not used Hund's rule yet. Everybody good right now? So I still have 18 left. What is the next orbital I will use?
2p.
2p. The 2p can hold how many? 6. So how many sublevels do I need? 3. So I will now go over here, and I will go 2p, 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 because each of those p's can hold how many? 2. Okay? And so I've got 18. So now I have to fulfill Pauli exclusion, and I have to fulfill Hund's. So now I'm going to go up, 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 before I can come back and add a second one going down, down, down. How many do I got left now? 12. Okay? You seen it? Like, I know some of you see it quick. Some of you say, I ain't seen nothing yet. Okay? Like, some of you are still stuck on this diagram. I don't understand how it lined up. All right? Are we done? No, because we still have 12 left. All right? Off-bow principle. Who's next? 3s. Okay, so now we're going to go to the 3s. Okay? 3s can hold 2, right? Well, I got 12. How many can it hold? 2? 1, 2. How many have I got now? 10. So whoever said 1 up, hopefully you better have that 1 down too. Okay, I didn't hear. I heard the 1 up. I didn't hear the 1 down. Okay, so I'm just making sure. All right, I still got 10 more. Who's next? 3p. How many can it hold? So how many do I got to write? 3. Because each can hold 2. So I got 10 that can hold in a spot that can hold 6. Up, 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 before I can come back and add the second one to each other one. How many have I got left? 4. All right. Who's next? 4s. Okay. By the way, ready? You know how simple it is when you have that diagram in front of you? Do me a favor. Is it on the reference sheet? So where should it be on test day? Where should it be on quiz day? Up here. Okay? So the next is 4s, which can hold 2. So therefore, 1, 2. All right, minus 2 leaves us with 2. Who's next? 3D. Okay? You good, JD? Well, when we follow the arrows, right? 3p, which is where we just were. Next is 4s, which is where we just were. And now we're going to backtrack and go over here, and we're going to go to 3D. Okay? So we're going to go to 3D. How many can the d orbital hold? 10. So how many d sections do I need? 5. So I'm going to go here and put 3D, 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 3D. Okay, I hear you, but I know they're still going to be there, right? Like my class has no students for a period. Does my room disappear? No, it's still here, just as empty. Okay, so I mean, I understand your point, so I'm not mocking you. I'm just saying. All right, so I got 2 left. Hold on, JD. I go over here and I go up, up, and then I'm out. And then we're done. And that is your orbital configuration notation. All right? I saw a hand go up, JD. That was yours.
No, you can answer it.
Okay, Carlos.
So that would be the answer.
That would be the answer to the orbital configuration for titanium.
Why is
Okay?
it 1 for 3D? Because there's 2 left.
Why is it 1 for 3D?
Yeah.
It's not, it's 2. There's a bar in the way that I had to go to the other side. All right? Everybody see that? That's an orbital configuration. A standard configuration is actually easy. I'm going to say easy. If you can do this, then the next one is easy. Okay? This is the more involved one. Let me go ahead and write down, though, the standard notation. Okay? The standard notation for titanium. By the way, go ahead and list it in your notes. This is titanium. So that way when you're doing it, you don't get confused. All right? That's titanium. So when I go in and do my standard, by the way, let me go ahead and I'm gonna write it under here. This is orbital. All right, that's orbital. This I'm gonna put underneath it. That's standard. All right. So what was the first orbital that I used in the orbital? 1s, right? All right. How many arrows do I have there? 2. So therefore, in the standard notation, I'm not going to write arrows. I'm just going to use an exponent. And the exponent tells me how many arrows I had in that section. Everybody see that? All right. What was the next orbital I used? 2s. So I come down here, 2s. How many arrows? 2. So I put a 2 there. Okay. Here's where there's a difference. So you might want to catch this one. All right. You might want to catch this one. Here, I go to the next one I use is 2p, correct? 2p. How many arrows on the 2p's? So I'm going to go here and write 6. I'm not going to break it up into its 3 parts in a standard. Okay? I'm not going to do that because I don't need to. All right? If I want to show spin and Pauli and Hund's rule, I use this notation. If I just need to know a standard notation, then I use this where I don't have to do arrows. I can just put a 6. I don't have to do 2p2, 2p2, 2p2. I'll just 2p6. If I wanted to see the 222, do that then.
Wouldn't it be, the next one would be 3s2?
Yes, because we have a 3s and there's 2. All right? And so when we keep doing this here,
3p6?
that's what your standard notation looks like. So if you notice, the standard notation is a whole lot cleaner, for you to do. But it's a whole lot cleaner and easier for you to do when you're looking at the orbital. You know what I'm saying? If you're not looking at the orbital, then you still got to go through the same process. You still got to figure out what is the next order, how many can it hold, and what would your number be. All right? But this here is your orbital notation. This here is your standard electron configuration. All right? And before I run out of battery, which I might have already, this is the ending of this video.